Hi, this is Professor Fernandez, and this is video 3 in lesson 5. Topic here is continuity at a point, and we are going to talk about an example from Calculus Simplified. The example here is 2.7, the 7th example in chapter 2. So the example says, take a look at the function graphed here, figure 2.3a, and figure out if it's continuous at x equals -1, 0, and 1. Okay, so this is really about a question about continuity at a point, right? So over here, box 2.2 in the book tells you the criteria for continuity at a point. I'm going to ignore this down here because this only applies when C is the right endpoint or when C is the left endpoint. C here being the x value we are approaching. But if we look back here, we're looking at -1, 0, and 1, -1, 0, and 1. None of these places are endpoints of the function, okay? So we're not going to talk about that part of the criteria down here. So then, great, we have less work to do. We just have to talk about this part. So what does it say? Suppose that C is in the domain of a function. Then the function is continuous at C only when three things happen. First of all, f has to be defined at C, right? F of C exists. That's kind of already implied in this statement, but it's nice to think about checking this explicitly. It's very easy to forget. The second one is the general limit, the two-sided limit, as x approaches C exists. Again, this means that it equals some number, right? If you get infinity right, then the limit does not exist. And the third one is that the number you got here and the number you got here is the same. Okay, so that was meant to be an arrow there, right? In other words, they're the same number. So you might be thinking that this is somewhat like the three-part criteria for determining whether the two-sided limit exists, okay? And we did that in this previous video, or the video prior to this one. So video 5.2, review that if you need some more review of two-sided limits when they exist and how do we evaluate them. We're going to need that because that's a second criteria here. So we're going to have to remember that this is itself a three-part check. So really, if you're doing continuity at a point and you're using the definition of continuity to figure out whether a function is continuous at a point, you have 3, 4, 5 things to check. And it sounds like a lot, but it'll actually go fairly quickly. So let's hop over to the first part of this question, -1, and let's look at all those criteria. Okay, so x equals -1. So I'm just going to look here, do my usual ribbon analysis, and I'm going to look, first of all, at the limits. So the one-sided limit from the left, the y values approach 1. So as x approaches -1 from the left, -1 from the left, the y values approach 1. Okay. How about from the right? As x approaches -1 from the right, the y values approach 0.5. Okay, already you can see, and this is why I said in practice, even though we have 5 things to check, in practice it goes faster. Because already you can see from these two that the general implies that the general limit, two-sided limit, does not exist. Okay? Remember that for the two-sided limit to exist, the one-sided limits have to exist. They do in this case. They're each a number. And they have to be the same number. They are not. So the two-sided limit does not exist. And because the two-sided limit does not exist, this second criterion here fails. So the function is not continuous at that point. Okay. So we're going to write all this down over here. Is it continuous at x equals -1? No. And we are going to put that over here. So no. Great, so now let's evaluate the next point. Maybe we'll get luckier on this second one. How about x equals 0? So x equals 0 is over here. Let me do my ribbon analysis. We'll draw a ribbon around 0. And then let's evaluate the left and right limits. So as we approach 0 from the left, the y value is getting close to 1.5. So f of x approaches 1.5. As we approach from the right, the y value also is getting close to 1.5. Great. So the two-sided limit as x approaches 0 of the function is 1.5. Great. So now the second criterion here is satisfied. So now we go off and we check the other two. first, down here, does f of 0 exist, right? What is f of 0? It is the y value at x equals 0. Okay, so the y value at x equals 0 appears to be 1.5. So that is a number that exists. Great. So that works too. And then last one, is the two-sided limit and the f of c value the same? And the answer is yes, right? These are both the same number. So this last criterion is also satisfied. So we conclude that yes, the function is continuous at x equals 0. Okay, and then one quick thing I want to mention here, just so that we can, tie things together, but also perhaps make things go a little faster. You can now understand and appreciate what continuity adds. Before, when we were just looking at two-sided limits, right? This is the second criterion here. We were looking about the y values that the function tends to. We did not care what the y value at x equals c was equal to, right? That's f of c. Notice that now continuity brings that into the picture, right? Continuity asks that f of c exists. Now we do care that the y value at least exists. And we also care that the y value equals the two-sided limit. So that's what makes continuity different from just evaluating a two-sided limit. And we're going to see that very clearly in this last example here. So what about at x equals 1, right? Let's do all of this over again. So I'm going to erase to 0 here, the 0 here, right? And then do the whole analysis over again. Okay, so at x equals 1, there we go. I'm going to draw my ribbon. There's the ribbon. And now let's investigate the limit. As I approach from the left, the y values are getting close to 0.5. So 1 from the left, f of x goes to 0.5. As I approach from the right, the y values again are getting closer to 0.5. 1 from the right, 0.5. Therefore, the general limit, the two-sided limit, exists, and it's also equal to 0.5. However, now let's go back and do the other criteria. What is the value of the function at 0.5? Now I don't need the ribbons. The value of the function at 0.5 is 1. Therefore, is the limit as x equals 1 of the function equal to the value of the function? Excuse me, this should have been 1 over here. F of 1 equals 1. Is the limit equal to the value of the function? The answer is no, right? So the value of the function is 1. The value of the limit is 0.5. Okay? So the conclusion over here is that no, the function is not continuous at 1. All right, so now we zoom out and we can explain this one visually as follows, right? The fact that the y values are tending to the same thing, right, 0.5, tells us that the general limit, the two-sided limit, exists. That's great, right? The y value at x equals 1 is also a number. That's 1. That's also great. However, those two y values, right, this one and this one are not the same. There is a little bit of a gap in those y values, right? So that's why the function is discontinuous. And now we can zoom out then and we can appreciate what happens. These are 3 examples here of continuity. In the first example, the function was discontinuous at the point because you had this jump, right? The function came from here and then jumped down over here. So that's that example. And then in the second example over here, we were looking at x equals 0, and you had a function that was just defined normally. The y values are normal in the sense that it was just, a function that's curving over here. So the left and right limits were the same, and they were equal to the value of the function at that point. Okay. So on the right side over here, we had something else of a discontinuity. We had the left and right values, left and right y values tending to the same number, so that's 0.5, but then that was not equal to the value of the function, right? So this is called a gap discontinuity, whereas this one was a jump discontinuity on the left. Great, so continuous at x equals 0, discontinuous at x equals 1, discontinuous at x equals -1.